let's talk about the concept of increasing and decreasing functions. So this is under differential calculus. Okay, so we already know how to determine the derivative of a function. So the derivative of a function can tell you whether a function is increasing or decreasing. But before we look at how, let's try to understand what it means for a function to be increasing or decreasing. Okay, so consider a linear function like this, and then consider another linear function from the other direction like that. So which one would you say is increasing and which one would you say is increasing? So we basically get to observe that by looking at the x-axis. So if you look at our x-axis, let's take this one to be maybe somewhere -4 and then this side +4. So the question that you need to ask yourself as you are moving from the negative x-axis towards the positive, what is happening to the y value? So obviously you can actually note that for this other one, as we move towards the right, the value in y is what? We can observe or note an increase in the value of y. In other terms, the function is increasing. But for the other one, where the value of y is kind of decreasing, we can see that there is a decrease in the function value. Okay, so this is basically what we're trying to say. Now, of course, if you try to look at the equations of these linear functions, it's an undeniable fact that if you try to determine the equation, likely the equation is supposed to be in that form for that other one, and then this one as well. Okay, so explicitly mentioning that for this other one, m is of a steepness is expected to be a negative, the other one positive. Okay, now we've also talked about the derivatives to say the derivative of a function can help you determine what? The gradient. We call it derivative function or the gradient function. Okay, so I think you've now gotten the point there. So you know what it means for a function to be increasing, and you now know what it means for a function to be decreasing. Now, of course, calculus is more concerned or interested in talking about curves that make it more interesting. So let's look at the curves and just basically see what we might expect. Okay, sorry for that. So if you talk about an exponential function, we know that an exponential function behaves in this way, like that. Okay, so you can see that as we move from the negative x-axis towards the positive part, the value of y is doing what? Is increasing. So that's an example of an increasing function. So that is of course e to the power x. Now of course we can also have another example of the logarithm function as well, something like this. So that is also another function. You can also see now that it's also what? The value of y is increasing as we move from the negative or from left to right. We can see an increase in the value of y. So that is also an increasing function. Okay. So examples of decreasing functions would be the ones where it's like going down as you move from the left to the right. Okay. It can be like this as well. The value of y is reducing as you move from left to right. That's what differentiates decreasing and increasing functions. Now, these are kind of perfect functions that we've talked about so far. Now, there are also some functions where it's mixed up. Depending on the range that you're talking about, the function behaves differently at different domains. So you can see clearly to say if we try to observe this function at this range, at this domain, we've seen that it's increasing by that line. Here you can see that it's decreasing continues to decrease there, and then again it starts to increase. So it depends on the kind of functions that you're talking about. So the domain also does matter. So now this is where we're going to be working with the critical points and stationary points to help us determine for certain functions where it is increasing and where it is decreasing. But of course, we've understood what it means for a function to increase or decrease. So I think this is going to be more interesting as we talk about curve sketching. That's why you understand to say, okay, a function can be increasing, decreasing, and be constant at given points. Okay, so theoretically talking, before we even head to curve sketching, let's look at a few functions and try to check whether they are increasing or decreasing functions in general. Let's consider a function y is equal to x squared. So this is a very common function. So then before we apply calculus, let's try to sketch it. So obviously you know that this is squared, so you don't expect to get any negative at any given any value of x. So this is how the graph is going to be. Okay, so of course one statement that you can notice, you can clearly see that as we move from left to the right before 0, what are we saying? The function, the value of y has reduced. So considering that domain, so from the negative infinity all the way up to 0, we can basically see that the function is what? The function is decreasing. And then after this, what can we see? So from 0 again increasing. So from 0 all the way up to positive infinity, we can conclude to say the function is now increasing. Okay, so with calculus, what you need to understand is when the derivative or dy dx is greater than 0, when it's greater than 0, or when you have a positive value in other terms, then you need to conclude that the function is increasing. In a case where it is less than 0, in such a case you conclude that what? The function is decreasing on that interval. Okay, so of course there are some cases where the dy dx will just be equal to 0, but we'll talk about that. For now, take it as greater than or equal to 0 to be an increasing function. Okay, a case where it is equal to 0 will make sense a bit later. Okay, let's move on to a different kind of a function where we have, let's change the power, let's make it the power 3. So this one is a bit unique compared to, since this one can accommodate both positive values. So when you're on the positive part, values will continue to be positive. Then as we go to the negatives, it will be negative values alone. So its function behaves like this, and then again behaves like this. So I actually didn't finish on the y is equal to x squared. So y is equal to x squared, if you differentiate it or determine the derivative, our dy dx is equal to 2x. So if you consider the part, of course the graph is something like this, okay? I hope you've not forgotten. For x squared, the graph is never cuts the negative part of the y-axis. Okay, so if you consider values less than 0 going this side, you can get a negative 1. You plug in the dy dx there. So if you plug in there, what do you expect? If you plug in a negative 1, the value will be a negative 2. So a negative value, remember I said when the dy dx is less than 0, then the function is decreasing. So we can clearly see that it's decreasing. Of course, if you get the positive part, you expect that it will give you as a positive value, which indicates that the function was increasing. Now, of course, I can now mention that if a dy dx is equal to 0, that is referred to as a critical point or stationary point. You understand what stationary points are? So stationary because the function is neither increasing or decreasing at that given point. Okay, so you understand. So y is equal to x to the power 3. If you look at what I've drawn here, what you might expect is after 0 going this side, positive from 0 to positive numbers, we can see that the function is increasing. As we move from the left again, we can still see that the value of y is still what? Is still increasing. So how do we tell? How do we know? So let's try to differentiate this function. So according to what we've looked at, we've seen that the function is purely increasing throughout. So dy dx, hopefully to confirm that, if you differentiate this function, we're going to add 3x squared. Now this is where it becomes interesting. Whenever you've got x or any variable raised to a positive even number, or let me just say positive power, not necessarily positive power, but an even power, 2, 4, 6, 8, and so on and so forth. In such a case, you can never get a negative, not unless if you have a negative coefficient. But in this case, it is just like that, 3x squared. So the values that you're going to plug in, whenever you plug in a negative where there is x, they'll continue giving you positive values. So even if you get the values less than 0, negative what, you raise with the power 2, it will become a positive. So here all values will always be positive, which clearly proves that this function will be increasing throughout. Okay, I think that's very cardinal and very important to just help you understand. Okay, so with linear functions, of course, it becomes very easy because you can just write it in the form of y is equal to mx plus c. So if you make y the subject here, you would have to divide by 4 throughout. So y is equal to, of course, take the other part to the other side, and then you have plus 7. So you can clearly see to say the gradient m there is a negative. So this is expected to be a linear function that is what? Decreasing. Even if you try to differentiate this part, y prime or the dy dx is just going to be negative 3 over 4. So a negative value indicates the function is decreasing. Okay. What about if you have certain interesting parts? What if you had f of x and then raised to the power negative x? I'm so curious to just try to understand how you would look at this. Would you say this function is an increasing function, a decreasing function, or what would you say? So let's try to determine the derivative. So you can not easily sketch this function, so let's try to determine the derivative. Now of course we understand we apply the would have to apply the product rule. We've got two different functions here. So I'll take the first one, x, I'll differentiate it, I'll get a 1, and then I'll multiply by the original other part, and then I'll start now by the derivative of e to the power negative x. So we said, how do you differentiate exponentials? So a derivative of an exponential, differentiate the power. So a power there, if you differentiate, you get a negative 1. So now negative 1 multiplied by the original itself. That's the derivative of an exponential function. Okay. Of course, you have to add the natural log of what? Natural log of the base itself, which in this case will just cancel out, and then multiply by now the original first part. So at this point you can factorize e to the power negative x, which I believe is common. For the first part you remain with a 1, the other part you remain with a negative, and then x. This is the derivative that you have. Okay. So one thing that you know is an exponential function, if you try to sketch it, it never cuts the x-axis. This is the way it behaves. It will always be getting closer and closer to x as you move towards the negative numbers, and will increase exponentially like that. So meaning that no matter what value of x you put there, the function is expected to never go to the negative values. Okay. Of course, a counterpart, natural log, behaves like this. Okay, that's why they're inverses. So in this case, what do we expect? So meaning that what is determining the sign or or any outcome of this function is purely what is in the brackets, which is 1 minus x. So we understand that if you get values of x that are less than 1, or values of x that are less than 1, all you're going to be getting is, so if you have x being less than 1, values that you're going to get will remain positives. And then if you get a value of x that is greater than 1, you will now begin getting negatives. For example, if you put a 2 there, you get what? You get a negative, right? Yes. So in a case where we're getting a negative where x is greater than 1, we can clearly indicate that within that domain, the function is said to be decreasing. And then in a case where the values of x are less than 1, we'll always get positive. So the function is now increasing in such a case. Remember, always from what is outside, you always be getting a positive. So what will determine the overall sign is what comes out from the brackets there. Okay, that's how you can look at such a function. Okay. So of course, I've mentioned we can also have cases where you have now a function which is, I think we've already encountered this. Yeah, I've already encountered this. But of course, let's try to look at this quadratic function. Let's try to differentiate it. So y prime will be 2x plus 4. So for this function, now this is where it becomes interesting, because how do you basically know or tell when we expect this function to be increasing or decreasing? So let's try by guessing first of all, and then I'll show you the simpler way of undoing it. So by guessing, when do we expect the what? When do we expect the dy dx of the y prime to be positive, and when do we expect it to be negative? Okay, so clearly, if I put a 2 there, or if I put a negative 2, I expect this is going to give me 0, right? Yes. So it's like negative 2 is like the deciding point, because that's why it's equal to 0. So what if I try to get a value greater than negative 2? Maybe a 0, a 1, a 2, and so on and so forth. So in such a case, if I get, for example, a 2, I put it there, I'll get a positive result. So going this side, I'm getting a positive result. If I go below negative 2, for example, negative 3 times 2 gives me negative 6 plus 4, which is a negative. So going this side, I'm getting a negative. So I would guess to say, okay, well, each time my value of x is less than negative 2, what am I getting? I'm getting a function that is decreasing. And then each time my value of x is greater than negative 2, what am I getting? An increasing behavior. So that's by guesswork. Now the simpler way of trying to approach this is where we introduce in what we now call the critical point. So the critical point is where you expect that the dy dx will be equal to 0. So 2x plus 4 becomes so equate whatever you've determined as your dy dx, equate it to 0. So 2x is equal to 4, negative 4. So x becomes negative 2. So that is always very important. So of course we'll look at cubic functions and other bigger functions where you are going to have more than a single critical point. And that is very necessary for you to determine the parts where the function is expected to increase or decrease. So if you have a critical point like this one, all you just have to do is try to now determine the behavior on the left and the positive side, of which we've already determined that. Of course, when you go to the side where it is less than negative 2, it's decreasing, increasing on the other end. Now, there will be interesting parts now where we have a curve like that. So such a curve is going to have critical points at that point, at that point, that point. So the way you basically get to look at this is, for example, you'd get this value of x there, maybe -4, and then 1, and then of course this is going to be done theoretically because it will not obviously be sketched. So you'd have to look at -4 and 1, and then you get any value, plug in the derivative function. If it obviously you expect that here to give you a positive value, here to give you a negative value. Okay, it will continue negative value and then positive value. So of course there are points where now at these points, now these points where which we are going to talk about are called stationary points, where now even the dy dx will be equal to 0. Okay, point like that one. Okay, so you understand. But for now, understand that we'll be using or determining what we are calling critical points to help us determine where parts of the function of a curve, where it is increasing or decreasing. And I think that is one of the key concepts that helps us to sketch a curve. Okay, let's proceed now and just get to look at the stationary and the critical points.